So our project was to create a geological linear actuator prototype. This is by Cody Price, Mariana Salazar, and Jonathan Fletcher Hall. Geode collecting is a passion that all three of our group mates share. That's exactly why we chose this project. Growing up, we all had some sort of collection of geodes. Usually you can get them, coming home from a trip from the mountains. We realized that it can be very difficult for someone to crack a geode, especially children and elderly people. And we want everyone to be able to follow their passion, no matter how old they are. So we decided to make this linear actuator. Its purpose was to crack geodes. Without being held down by the user, the geode will be able to be cracked, which increases the factor of safety. Normally when cracking a geode, you have to hold it with one hand, take a hammer, a pipe, something heavy, and hit it until it cracks. It is very possible to hit your hand and cause an injury, and that is something you do not want to do. The linear actuator will have a higher precision and force, which will allow for a cleaner break in the geode. So our experiment consisted of 3 phases. We had the assembly phase, the programming phase, and the experimentation phase. Here you can see our Arduino Uno and our DC controller, 2 parts that you're about to learn more about. So in our assembly phase, we've had dynamic and mechanical parts, a whole lot of them. The U channel is the frame of the actuator. The X rail is an extension tube supported by 2 acetal plates mounted to the frame. There are 2 48-tooth gears. One is mounted to the motor, and the other is mounted to the X rail. The motor, which you can see listed here, is mounted to the side with a 32mm aluminum clamp, which keeps the motor in place while it's running. Here you can see the X rail before it's extended, and then here you can see the X rail after extended, as well as the 48-tooth gears. There's a whole lot of programming and electrical chip that also had to go into this project. We used a mini Linux-based computer chip known as the Arduino, but more specifically, that I showed you earlier, the Arduino Uno. We used a DC motor controller, a Bluetooth chip, and an 11.1 DC battery. Here you can see the Bluetooth chip. And then here you can see the full assembled actuator. So now let's talk about programming. In order for the motor to work at varying speeds and extrusion lengths, some programming was necessary for the Arduino and Bluetooth chip. The program shown here is what allows the motor to change velocity and extrusion length. The motor is given a numerical speed and extrusion length with a dead zone to prevent it from burning out if the extrusion length is at its maximum. The motor is capable of running 1150 RPM, which is equivalent to 120.43 radians per second. At maximum speed allowed, the X rail will have a velocity of 6 inches per second and a maximum force of 50 pounds, and this converts to about 220 newtons. The actual value we used during the experimentation was 60.2 radians per second, or 575 RPM. Here you can see the governing diagram. We used 8 trials with increments of 12.5% to test the gear slippage and to see what our best power rate would be. Our calculations showed that the most effective rate would be half of the maximum angular velocity, which is correct based off of our trials, because at any rate higher than 50%, the gears slip more, and under, they all slip the same. It was also found that the geological linear actuator was more effective at lower speeds, and even at lower speeds, it still has the same force output. It just moves slower. So for our results, it ends up that breaking a geode proved to be much harder than we thought, even with the mechanical help. We were unable to break the geode with our actuator because the motor just was not strong enough. There could have been some human error in there as well when it came to our hand calculations. So maybe, the force just wasn't right. So in conclusion, we found great success in the actual building process of the actuator, but the programming is where we struggled, which is exactly what you'd expect out of 3 mechanical engineering students. After completion of this project, we would recommend using an air compression system over using an electrical motor. The motor we used honestly just wasn't powerful enough to break the geode, and it is not feasible for real-world application, at least what we did.